Hello friends, welcome to Susan and John MathTube. From today onwards, we start with a new topic, complex analysis. Complex analysis is very important for mathematics major students and applied mathematics students. And when we think about applied mathematics students, it's like extra important for the engineering students and the physics major students. To understand complex analysis properly, we should be well prepared with the basics of complex analysis, that is, the complex numbers. And in this video, we will make the foundation of complex analysis very clear. So let's start with complex numbers. Okay, so the story goes like this. Suppose I want to find root under 9. Then you will be searching for a number whose square will be 9. So I get the answer 3. At the same time, if I ask you what is root under minus 9, you may not be able to answer. And to solve this problem, what we do is, or what mathematicians do is, they call root under minus 1 as I. Originally it was called iota, but there is no harm in calling it I. And by defining root under minus 1 as I, we have solved the problem by writing minus 9 as minus 1 multiplied by 9. And that means I'll be able to write root minus 1 multiplied by root 9, and that gives me the answer I multiplied by 3 or 3I. And such numbers are called imaginary numbers. Just like our real numbers like 1 by 3, 1 by 2, 7, minus 2, just like our real numbers, now we have a new set of numbers called imaginary numbers. For example, suppose I want root under minus 16. We follow the same process and eventually I get the answer 4 multiplied by I. So I am able to create the square root of negative numbers, and those numbers are called imaginary numbers. Now look at this. I am able to add a real number with another real number. For example, if I add 4 and 3, I get 7. Similarly, I will be able to add imaginary numbers with imaginary numbers. For example, 2i plus 5i, something plus 2 apple plus 5 apple gives me 7 apples. So similarly, we are able to add imaginary number with another imaginary number. But now look at the problem. I will never be able to add a real number with an imaginary number. Hence, we get a new type of number system and we call them the complex numbers. So, every complex number will be in the form x plus iy. So, generally speaking, every complex number will be in the form x plus iy, and usually we use the letters z and w to represent complex numbers. By the way, don't forget, this is called the real part. That means x will be called the real part of the complex number and y will be called the imaginary part. So if I write RP, real part of z, you have to understand I'm talking about the part without I, the real part. And if I ask you the IP, the imaginary part, some people write RE and IM, and that will be Y. We have the complex number. So point number 1. It will be nice if you note down these points. Point number 1. To plot the complex number, we use the Cartesian coordinate system. and we imagine the complex number is a coordinate x comma y, and we find the coordinate x comma y, and this will be the same as x plus iy. And if you are plotting the complex numbers in the Cartesian system, then the system will be called Argand diagram. What do you call it? The Argand diagram. But some mathematicians love to express the complex number as a vector. And when they try to express the complex number as a vector, we actually get the polar form. Do you remember? We have two standard systems, the Cartesian system and the polar coordinate system. So if you write a complex number in the polar coordinate system, you believe that this is a part of an imaginary circle with radius r, and this angle is called the argument. So the same coordinate can be represented as r comma theta. So once more, point number 1, we found that negative numbers have square root. How do you find the square root of minus 3? Very simple. You find the square root and multiply it by I. Suppose I want root under minus 64. Very simple. You find the square root of 64 and put an I. Point number 2. We are not able to add the real number with an imaginary number, and we ended up with the complex number. And we denote the complex number by the letter Z or W. The complex number can be converted into a graph by means of the Cartesian coordinate system by marking the complex number as x comma y. And if you do this, the system will be called the Argand diagram, and the x-axis will be called the real axis, and the y-axis will be called the imaginary axis. Another method is you just write the length r and the angle theta, and you can call it r comma theta. If you do this, it is called the polar representation of the complex number. So you have to understand, a complex number can be written as x plus iy, and it can be converted into r comma theta form. And in 10 minutes, we will be learning about how we can convert it into the polar form. Okay, now second thing. Suppose someone asks you to find Z bar, or in some books they use Z star. This is called complex conjugate. What do you call it? Complex conjugate. And the idea is very simple. Replace I with minus I. What will you do with I? Replace it with minus I. So if I want the complex conjugate of 3i plus 7, all I have to do is I have to write minus 3i plus 7. If I want the complex conjugate of e to the power ix, all I have to do is I have to write e to the power minus ix. So complex conjugate means you replace I with minus I or minus I with I. Just change the sign. Now the third thing you have to understand is the modulus of the complex number. By the way, modulus means length of the complex number. Look at this. Suppose I have a complex number x plus iy. I will be able to plot it in the graph by marking this length as x and this as y, so that the length of the complex number as a vector will be root under x square plus y square. So modulus is nothing but the square of the real part plus the square of the imaginary part. Suppose you want to add two complex numbers. It's like very easy. Add the real parts plus add the imaginary parts. Suppose you want to multiply two complex numbers 4 plus 3i multiplied by 1 plus 2i. Just distribute the numbers 4 and 3i. So what is 4 multiplied by 1? What about 4 multiplied by 2i? Now what about 3i multiplied by 1? And finally, what about 3i multiplied by 2i? That will be 6i square. By the way, I hope you still remember root under minus 1 is I. So that I square will be equal to minus 1. So don't forget this result. I square is minus 1. So this simplifies to 4 plus 11i minus 6, and we end up with minus 2 plus 11i. So that's like very simple and natural. You can add complex number, so obviously you can subtract. You can multiply complex numbers, and remember I square is you want to divide two complex numbers, something like 3 plus 4i. Always remember your job is to remove I from the denominator. What will you remove? Remove I from the denominator and put it in the form x plus iy. And the method is very easy. All you have to do is multiply the numerator and denominator by the complex conjugate of the denominator. I hope you still remember the complex conjugate. What do you mean by complex conjugate? Replace I with minus I or minus I with I. Now that's it. Multiplication. You know how to multiply the numerator. I hope most of you know the result. X plus y multiplied by x minus y. It's simple distribution. It gives you x square minus y square. So this 3 plus 4i multiplied by 3 minus 4i. If you want, you can distribute it. But I know this result, so I'm going to get 9 minus 16i square. I hope you still remember root under minus 1 is our I or iota. So that I squared will be minus 1. Never forget I squared is minus 1. So we can simplify this. 9i minus 4i will be 5i, and this simplifies to plus 12. The whole divided by 9 plus 16. So you get 15 plus 5i divided by 25. And then you have to split it. 15 by 25 plus 5 by 25i. You can simplify this into 3 by 5 plus 1 by 5i. We have the complex number, then the complex conjugate, then the modulus. Next thing, every complex number can be converted into a graph by means of the Cartesian coordinate system, but it will be called the Argand plane or the Argand diagram. And if you use the length of the vector and the angle made by the vector, it will be called modulus argument form. Next, we can add, we can subtract, we can multiply, and when it comes to division, never ever forget you have only one job. Remove I from the denominator. And how do you achieve that? Very simple. You multiply the numerator and the denominator by the complex conjugate. I hope you are not lazy. So keep a paper and a pen and work out these problems. Unless and until you're good with the foundation, you will not be able to climb the ladder in complex analysis. Okay, so let's move on. Let's go for the next part. This is extra important. You have to learn how to convert complex numbers from Cartesian to polar form. Don't forget, Cartesian form means suppose I have a complex number 3 plus 4i. So what I do is I convert this into 3 comma 4. So I'll mark 1, 2, 3 and I go up 1, 2, 3, 4. So this is my complex number 3 plus 4i. Now the vector diagram gives me the same complex number like this. And I can find the length, that will be root under 3 square plus 4 square. Do you remember? Modulus means the length of the vector. And I can also find this angle. Can you see? I can find this angle. And by calculation, I know it is like tan inverse. This length is 3, this length is 4. So the basic trigonometry tells me this angle will be tan inverse 4 by 3. So the same complex number can be converted into, what is root under 3 square plus 4 square? 5, comma tan inverse 4 by 3. If you are able to write like this, it is called the polar coordinate form. So look at this, 3 plus 4i can be written as 5 multiplied by cos theta plus I sin theta. This is called the modulus argument form. Some authors love to write this as cis theta, C for cos, I for iota, and S for sin, and they write theta. In this problem, theta is tan inverse 4 by 3. And Euler, a mathematician, he found that this can be written as e to the power I theta. Okay, let's go in detail. Suppose we have a complex number in the Cartesian form. Now I'll give you a trick. Note it down. This is going to be extra important later. So suppose I have a complex number x plus iy. You have to understand that this can be converted into r theta form. That means the same complex number can be written as r e power I theta, or you can write this as r into, because e power I theta is cos theta plus I sin theta, or you can write this as cis theta. So remember 1, 2, 3, 4 all are same. Okay, and the trick, now I am not going to give you any logic or anything, a trick. Suppose our Cartesian complex number is in the first quadrant, then theta is given by tan inverse the positive value of y by x. If it is in the second quadrant, then it is given by tan inverse mod y by x, but I am going to subtract it from pi. Once more, I am not giving the logic, just learn this as a technique, because you are supposed to learn all this stuff in your high school. And if you have a complex number in the fourth or the third, it's very simple. It will be negative of what you saw here. That will be pi minus tan inverse mod y by x, and here theta will be minus tan inverse mod y by x. So it's so easy to study. Let's do one problem, otherwise you may not understand. Suppose I'm going to give a complex number 1 plus I root 3. I want a quick method so that I can convert this into the polar form. I want a super quick method so that I can convert this into the polar form. So all I have to do is I have to find r and theta. Very simple. R is given by root under, come on, r is the modulus, the length, 1 square plus root 3 the whole square, and that will be equal to 2. Now for theta, I have to understand the quadrant. Look at this. This is 1 comma root 3. 1 comma root 3 is in the first quadrant. So theta is given by tan inverse modulus means positive value, root 3 divided by 1, and using a calculator or from my basic mathematics, I know this is 60 degree or pi by 3. That's it. Now look, I can write my complex number is equal to r e to the power I pi by 3. Or I can write the same stuff as 2 multiplied by cos pi by 3 plus I sin pi by 3. Or I can write the same stuff as 2 cis pi by 3. I'll give you one more example so that you become more familiar. This time let's go for 1 minus I. So look at this. 1 minus I is 1 comma minus 1 in the argand plane. And where is 1 comma minus 1? 1 comma, okay, it's in the fourth quadrant. So r is equal to root under 1 square plus minus 1 whole square, that will be root 2. And theta will be, come on, I told you, all you have to remember is theta is tan inverse mod y by x, and just below it will be the exact negative. In the second quadrant, you have to remember pi minus, in the quadrant below, it will be the exact negative. So I'm going to calculate theta, that will be minus tan inverse positive value of y divided by x. That means minus tan inverse 1. And that will be minus pi by 4. That's it. Now I can write 1 minus I equal to r e to the power I into minus pi by 4. I'll give you one more question, and with that we will wind up this video. Convert into modulus argument form minus 1 plus I root 3. Come on, super fast. This is minus 1 comma root 3, and minus 1 comma root 3 means it's in the second quadrant, and r will be root under minus 1 the whole square plus root 3 the whole square, and that will be 2. And theta will be equal to, come on, tell me what's theta? Pi minus tan inverse mod y by x. So pi minus tan inverse positive value of root 3 by minus 1. So that will be pi minus tan inverse root 3. Because I have to take the positive value, that will be pi minus 60 degree. And that gives me 2 pi by 3. So I get the answer minus 1 plus I root 3 is equal to r e to the power I 2 pi by 3. So easy. Okay, so once more, let me make it very clear. A complex number can be written in the form r e power I theta. And that is the same as, what is r e power I theta? Cos theta plus I sin theta. And this can be written as r cis theta. Okay, and don't forget, theta is called the argument, and argument is given by tan inverse y by x. And another word for argument is amplitude. Okay, so we will wind up this video here. So if you like this video, share with your friends, and I'll be back very soon with another video in which we'll be talking about complex function. So till then, my friends,